Hello, I am Seema and welcome to part 17 and the last part of the chapter, Chemical Kinetics. In this video, I am going to tell you about the collision theory of chemical reactions. We have studied about the Arrhenius equation and how Arrhenius assumed that the energy of activation was the most important factor that affected the rate of the reaction. And on the basis of that, he gave this equation, that is rate constant K is equal to A into E to the power of minus EA upon RT. This was known as the Arrhenius equation, where A was the Arrhenius factor, K was the rate constant, and E to the power of minus EA over RT was that fraction of molecules which had energy greater than the energy of activation. And only then, if the molecules had energy greater than the energy of activation, would the reaction proceed towards formation of products. Therefore, the speed with which that would happen depended on the energy of activation. Higher the energy of activation, obviously more energy is required for the reactants to get converted into products. Therefore, it is more difficult, it takes longer time. And with the use of a catalyst, as I showed, the energy of activation decreases and therefore it becomes easier to jump over the energy barrier and therefore it affects the rate of the reaction, and addition of a catalyst increases the rate of a reaction. Now, there were two scientists Max Strauss and William Lewis, and in the years 1916 to 18, they had insights, or they gave insights into the energetic and mechanistic aspects of chemical reactions, which means that they went ahead even further than Arrhenius and focused into the factors that affected the rate of reaction and realized that it is not just energy of activation which will determine the rate of a reaction. There were other factors which could influence the rate of reaction. And these factors, what was their nature? It was energy, that there was some other thing about energy that they had to know, and the mechanism of the orientation, that how is the molecule going to approach each other, that would also determine the rate of reaction. So they went deeper into the study of the rate of reaction and found out other factors that affect the rate of reaction. And on the basis of that, they gave this theory which was known as the collision theory of chemical reactions. When you say collision, you remember in the kinetic molecular theory of gases, we assumed the gaseous molecules to be spheres, and we assumed, when we were talking of states of matter, and we assumed that these spheres, they come and just collide. The gaseous molecules, they come and collide with each other, and these collisions are perfectly elastic, no exchange of energy takes place, and therefore that was our description of an ideal gas. And we know that never happens. First of all, molecules are not spheres. Second, if they collide, there will be some exchange of energy. The same thing, they just to simplify and understand what would be the factors that would affect, they assumed that the molecules, the reacting molecules, they are spheres. And these spheres, they cannot react. Now, one sphere is sitting here and one sphere is sitting here. They're not even talking to each other. How can they react? They cannot react unless and until they come and collide with each other. So that was the basis of the collision theory, that only the reactant molecules, in order to react, must first come in physical contact with each other, which they called a collision. So they said the reactant molecules were assumed to be hard spheres, and it was assumed that only when reactant molecules collide do reactions take place. And the rate of the reaction will depend on how frequently the collisions take place. So this was known as collision frequency, and it was represented by the alphabet Z, capital Z. So collision frequency, or Z, was the number of collisions per second per unit volume of the reactant solution. Now we already are aware that there is a factor, another factor that affects the rate of a reaction is the energy of activation, which Arrhenius has already told to us in details. We've studied about it in details about the Arrhenius equation and how it says that the rate of the reaction depends on the energy of activation. Now let us assume an elementary reaction. So the elementary reaction has A plus B. An elementary reaction is, if let us say there's a complex reaction, one of the steps of the reaction of the complex reaction would be an elementary reaction, a reaction in which you have one or two reactants and nothing more than that, a simple reaction. So if you take an elementary reaction where you have A plus B other reactants which are giving you products, it is bimolecular, there are only two molecules A and B, and it is an elementary reaction. According to now Max Strauss and William Lewis, how did they give the expression? The expression they gave for rate was equal to ZAB, where A and B are the molecules of the reactants and Z is the collision frequency. The collision frequency of the alphabets of the reactants A and B into e to the power of minus EA upon RT. Now if you carefully look at this, this is very similar to the Arrhenius equation. Arrhenius also said that rate, which was equal to K, was equal to A into e to the power of minus EA upon RT, and e to the power of minus EA upon RT is identical, rate is the same. The only difference is that you could substitute A with ZAB, isn't it? It is basically the same, only when we said this is Arrhenius factor, the Arrhenius factor was now being described by the collision theory. That it was the collision frequency or the frequency of collisions or the factor Z between the molecules of the reactants A and B. So this equation, it predicts the rates of reactions quite accurately when you have elementary reactions. When you have simple elementary reactions, this equation could be used, and it was giving the right reading for the rate of the reaction. But the moment a reaction became complex, the value of the rate of the reaction that you would calculate using this would be there would be a wide deviation. It would start deviating from the theoretical value that you would calculate and what the rate of reaction actually was. Therefore, although this equation, the collision theory, was applicable to simple reactions, it was not applicable to reactions that were more complex. So there was something else definitely affecting the rate of reaction which we were not noticing because the reaction was simple, and this factor came into play when the reaction became more complex. So this equation predicts the rate constants fairly accurately for reactions involving atomic species or molecules. When you have just atoms or molecules and elementary reactions, it would give this theory was applicable, but it showed significant deviations are observed for complex reactions. As soon as you get a complex reaction, the deviation is not just little, it is significant, it is noticeable. So which shows that this theory was not applicable to complex reactions. So only, what are the factors then? What did they notice? What did they realize? That when we say that collision frequency, the more the collisions, the more the reaction would take place. But no, in a complex reaction, the number of collisions is far more because there are more reactants, and more than two, maybe 3, 4, and of course the collisions are far more. Now, I have to be friends with you, and there are 5 people in the room, and I'm going and talking to the other 3, but I'm not talking to you. The idea is that I become your friend. Will I know you unless and until I talk to you? If I keep talking to the other 3, there is nothing that is happening between you and me. That is what happens. Collision frequency. I am colliding with 3 other molecules, but I'm not colliding with the one that I have to react with. So collision frequency may be important when you have only two reactants, obviously, because those are the molecules that are bombarding, they are touching each other, they are coming into contact. But if the molecules are not coming into direct contact and are coming into contact along with other molecules and not with you, obviously you two were supposed to react, you will not react. So it is not just the collision frequency. Out of all these collisions, not all collisions will lead to reaction. Only those collisions will lead to reaction where the orientation is right. If I am facing you, you are facing me, we two are talking, and we were the actual reactants for that particular elementary step, only then the reaction would take place. Although you were colliding with the other three, I was colliding with the other three, you and I did not talk to each other, so how would we be friends? So the bond of friendship would not be formed. So he said that only collisions which have, now there was another point, you remember I told you it was energetic and mechanistic. Mechanistic part was that they said that only if they have the proper orientation, when the collision takes place in the proper direction, only then the collision will be effective. That is, it will lead to the formation of a product. Secondly, the kinetic energy of all the molecules that are reacting, even if the orientation was right. You and I, we were to be friends. You and I were reactants and we were to be friends, and only if you and I talk to each other would we be friends. The one factor I just explained, that the orientation was wrong. We were going and colliding with other molecules, and therefore we were not colliding with each other, therefore the reaction would not take place. The other thing is that finally we do come together and we are talking to each other. But I am simply not in the mood to be a friend with you. That is how I am. You and I may, if we react, we will result in the formation of the product, but no, I will not do it. I'll simply not do it. Doesn't that happen? If you want a child to, let us say, study chemistry and clear the exam, and the child, there is one of them, if you and I work together, you would be successful, you would be able to study the subject, but you decide you're just not going to do it, come what may. You're not doing it. So unless and until you have that urge, there is a minimum requirement of energy. And let's take another example. I force, as I gave you that example, that there are 30 students in a class and we tell all of them are going to participate in a race. So all of them run, some come fast, some are slow, some are in between. What about that one odd student who is not well today? And he cannot forget about participating in the race, he cannot even stand. Maybe he's in the medical room somewhere. What about that student? Even if the reactant is there, if it does not have that minimum energy to even walk, how is he going to participate in the race? The same thing, that the molecules, even the ones who have to react, must have a minimum threshold energy. When you say threshold, that at least it should be capable of reacting. Only then will you give him the activation energy. Okay, come on, get excited. That is giving energy of activation. Then get ready. You will fill him up with the activation energy only if he at least has that minimum energy to stand up and walk. So that is known as the threshold energy. So he said that collisions would be effective or would lead to the formation of products only if the molecules at least had kinetic energy greater than the threshold energy. And the second factor that was described was that not only this, they should also have the proper orientation. Now when you talk of orientation, this is a friendship. Okay, you want to break the friendship. If I want to break the friendship, I should hit here where it is holding, where the bond is there. If I hit in this direction, the bond will break. But if this is the bond, and I come and I hit here, I'm only bringing them closer. I'm pushing the bond here. They will move here or there, but the bond will not break. The bond will only break if I hit where it is bound, right? So the direction in which the collision takes place, that molecule comes and hits in this direction. It is not going to form a bond in that direction. It can only form a bond if it breaks this bond and then takes its place with one of the reactants. One of the atoms. Therefore, not only should it have minimum threshold energy to react, it should also have the proper orientation which would lead to the reaction. And these were the factors that were not considered by Arrhenius. He only talked of the energy of activation. So proper orientation leads to reactions. Such collisions that lead to the formation of products are called effective collisions. So collision frequency, we may say yes, lots of collisions may take place, but only effective collisions will lead to the formation of products. And what is an effective collision? An effective collision will be one in which the molecules, the reactant molecules at least have kinetic energy greater than the threshold energy, and they collide with each other with proper orientation or in the proper direction. Let us take one example that is given in your book. You have the formation of methanol from bromoethane. Bromomethane. This is bromomethane, right? It's not ethane, it should be bromomethane. M should be added here. Now you have bromomethane here, and this is the OH negative ion. If OH negative, bromine is also negative, and OH negative is also negative. Now if you want to replace, this is the bond, it's the same situation. If OH, this is Br negative, and OH negative is supposed to break the bond. If OH negative comes to Br negative and it tells, hey look, move, I want to take your place. Both of them are negative. There is a competition that is built up. Both the negatives will repel each other. The Br negative is going to say, what do you think? Why would you take my place? And why would I let you take my place? Move away. And Br negative will repel the OH negative and move it away. But if OH negative was smart enough, or it had that minimum threshold energy and it decided not to come and talk to Br negative, but to come and talk to CH3 part. Look, you are positive in comparison to Br negative, and I am better than Br negative. Let's do one thing. You forget him, you forget Br negative, let us form a bond. Under that condition, the bond becomes weak and it breaks, and CH3 decides that, okay, not in this direction, let us make a friendship in this direction. So it breaks the bond, makes the friendship in that direction with OH negative. So the orientation is important. In the first case, the orientation was wrong orientation. OH negative came to the direction of Br negative. Both of them are negatively charged, they repel each other. There is no chance that OH negative can even come close enough for a proper effective collision. Even if it forcibly collides with Br negative, both are negatively charged, the repulsion will push it away. So the reaction would not take place, rather the products will move away from each other. So that is what happens. Br negative and OH negative, both of which have delta negative charges, both of which are negatively charged, they experience repulsion. If the orientation was right, the OH negative came towards CH3, then an intermediate will be formed. CH3 is already friends with Br negative, but the OH negative on this side is also interesting, so why not talk to him? So he starts talking to OH negative, and as the friendship with OH negative increases, the friendship with Br negative decreases, and that leads to the formation of an intermediate. And once the intermediate is formed, the Br negative, it moves away, resulting in the formation of CH3OH, that is methanol, from bromomethane. So isn't it interesting that unless and until there was that minimum threshold energy and the orientation was right, and then the Arrhenius equation that I told, that the energy of activation. So if you really look, there are three factors: the energy of activation and the collision frequency. But in collision frequency, you need effective collisions. What are those effective collisions? They depend on the threshold energy and the orientation. So to account for these other factors, another factor was introduced in the equation. And another factor in the collision theory equation, that is rate is equal to ZAB e to the power of minus EART. To this, the factor P was introduced, and P was called the probability factor. That there are so many collisions that are taking place in all, but out of these, the probability of only these many is effective. Only these many may be effective. So that probability of the effective collisions has to be introduced, and therefore that factor was added to the equation. So rate now becomes equal to P into ZAB e to the power of minus EART, and where P is the probability or the steric. When you say steric, you're talking of the direction, the orientation. The steric factor. That not only is it the number of collisions and the energy of activation, it is the direction of the collision, and of course the basic requirement for any reaction would be that the reactants should have the minimum threshold energy. Therefore this also contributes towards the probability factor. That what is if there are some molecules which are just not going to, do not even have that energy to react, obviously they would not be contributing towards the reaction. There were drawbacks to this theory. The drawback mainly was that just as in the kinetic molecular theory of gases, where we got the ideal gas, we assumed the gaseous molecules to be spheres. Here also, initially when Max Strauss and William Lewis gave the theory, they assumed the molecules, the reactant molecules, to be spheres. Later they started talking of orientation. Spheres do not have orientations. A sphere is symmetrical, and how do you talk of orientation in the case of a sphere? So this, you could say, was a drawback, that at that time they did not take into account the shapes of molecules. For that, you would have to go into deeper and more advanced study. So this was more elementary at that time. So we would say, what was the drawback? This theory considers molecules to be hard spheres, and it ignores the structural aspect. Now this is just fault finding, Later, when you do take those things into consideration, of course, how else would we have gotten the steric factor? So those details you would study at an advanced level. So with this, I finish this chapter. If you found my video helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.